Welcome back, everyone. In this video, we're going to start looking at Chapter 6 from the ebook, looking at chemical bonding. After reading the lessons and watching this video, you should be able to describe the three different types of bonding and determine whether or not a compound is ionic or covalent. And then, if you're given a chemical compound formula, you should be able to name it, and vice versa. You should be able to write the formula given the name, and then be able to predict the formula and charge using the periodic table. So we need to revisit a little bit of what we talked about earlier. And we discussed when looking at how elements form ions, they tend to do so such that they have a completed octet, or in other words, they have the electron configuration of a noble gas. And we see that metals tend to lose electrons, nonmetals tend to gain electrons, and the number that they gain or lose will be a function of how many electrons are needed to either lose or gain to obtain that noble gas configuration. So take hydrogen, for example. It has one electron. It needs to gain one more electron to obtain the configuration of helium. So it can either gain one electron and be H minus, or we will see that it loses an electron, having none. Lithium has one valence electron, 3 total, and so it will lose its one valence electron to obtain the configuration of helium. Beryllium will tend to lose 2 electrons, etc. Whereas on the right side of the periodic table, those elements, it's going to be easier for them to gain 1, 2, or 3 electrons in order to obtain the noble gas configuration. And what these structures here are what we refer to as Lewis dot structures. They show the number of valence electrons that an element has. We've talked already about bonding types and how we can have ionic and covalent bonding. A third type of bonding is known as metallic bonding. And so I want to review these different types of bonding with you. Ionic bonding occurs when we have oppositely charged ions that typically consists of having metals with nonmetals. The one major exception to that is with the ammonium cation. Ammonium consists solely of nonmetals, but because it's a cation, it behaves like other cations, like other metals, and will form ionic compounds. Some examples of ionic compounds are listed for you on the screen. Covalent compounds are where the electrons are shared between the elements in the molecule. This occurs when we have nonmetals bound to nonmetals. And then the final type of bonding is metallic bonding. This occurs only in metals, and this is when the electrons are more free to move around the atoms. And that happens because there are not enough electrons total for all the atoms, and so they will kind of slosh around. We're not going to get into great detail about metallic bonding. All you need to know is that it exists at this point. Now, let's practice. Which of the following features features both ionic and covalent bonding? Since we've already talked about this in previous videos, I want you to try this one on your own. So pause the video now and try. Welcome back. So we want to know which of these contains both ionic and covalent bonding. Well, the answer is calcium carbonate. Now let's talk about that. In order to have ionic bonding, we need to have a metal with nonmetals. In order to have covalent bonding, we need to have at least 2 nonmetals bound to each other. So when you look at calcium carbonate, we have the calcium ion, which is a metal, and the carbonate anion, which is a group of nonmetals, and therefore there exists an ionic bond between them. However, within the carbonate, we have covalent bonds between the carbon and the oxygens, and that's due to the fact that they're both nonmetals. So this has both ionic and covalent bonding. If we wanted to classify the others, this would purely be covalent bonding. Remember, hydrogen is a nonmetal. Sulfur tetrafluoride is only covalent bonding. Ammonia is only covalent bonding. And potassium bromide is only ionic bonding. Let's talk a little bit more about ionic bond properties. So ionic bonding is when we have electrons that are transferred to form separate ions. So the element that is going to form the cation donates its electron to the element that's going to form the anion. And this, so we end up with positive and negative ions. And the resulting compound must be neutral. This is important because this is how we are able to predict what proportions given elements combine in order to form ionic compounds. So sodium and fluoride, both as ions, have a negative or have a magnitude of 1 for their charge, positive 1 and a negative 1. So they combine in a 1-to-1 ratio. Potassium has a positive 1 charge. Sulfate has a 2- charge. Therefore, in order to balance them out, we need to have 2 potassiums for every 1 sulfate. Magnesium has a positive 2 charge, and each nitrate has a -1 charge. Therefore, we need 2 nitrates in order to balance out the charge and have a neutral compound. And as we've already mentioned, ionic compounds are made from combining metals with nonmetals, usually. The only exception to that that we are going to focus on is the ammonium ion. Again, this behaves like a cation, like a metal. And some properties of ionic compounds is that they tend to have very high melting points or boiling points and tend to be very brittle. Now let's talk a little bit about naming ionic compounds. You should review the stop sign in lesson 6-2 of the ebook to learn more about naming ionic compounds. This is just a brief overview. When we name an ionic compound, what we end up with is the combination of the name of the metal and the nonmetal. So if you know the name of the metal, cation, and the nonmetal anion, then you know the name of the ionic compound. For the cations, we can either have a case where we have the main group metals or the transition metals. Main group metals, it's just their name, lithium, calcium, etc. The transition metals, it's a little bit more complicated. And the reason for that is because they can have a variety of charges. And so we have to have a name for each charge of the transition metal. So you can use a Roman numeral designation or change the ending of the name. And in some cases, we will see that there are Latin names that are used. A very common one for that is iron. So iron, instead of being ironous or ionic, it is ferrous or ferric ion. And so, for example, we could have chromium 2 or chromium 3. That's using the Roman numeral designation. Or we could use the chromous or chromic ion designations to indicate that we're talking about which charge we're talking about. Then for the anions, most of them, all of the monoatomic anions and a couple of polyatomics will end in "ide." So examples of that include chloride or cyanide, fluoride, etc. And then most polyatomic ions have alternate endings depending on the structure. And we're not going to go into much detail about that in this video, but you need to realize that the structure will dictate its name. So let's practice here. We have CaF2. This would be calcium fluoride. The name of the cation followed by the name of the anion. Notice that we're not indicating how many fluoride ions there are. That's implied because the charge on calcium is fixed. Okay, LiClO. This is lithium hypochlorite. Lithium, the group 1A metal, and then hypochlorite, which is one of the polyatomic anions. And then this last one. This one could be either iron 2 chloride, using the Roman numeral designation, or ferrous chloride, using the Latin name with its ending. All right, now I want you to try and do some problems on your own. So pause the video and try and determine the names of those 3 compounds listed, as well as writing the formulas for those combinations. Welcome back. So remember that naming involves knowing the names of the cation and then the anions. So this first one here, this is going to be sodium oxide, COBr3 is, we could call it cobalt 3 bromide, or cobaltic bromide. And then MgI2, that is magnesium. Magnesium has a fixed charge, so we don't need to indicate what charge it has. Magnesium iodide. Hopefully you got all 3 of those. And then if we want to combine aluminum and sulfur, you would need to recognize that aluminum has a 3+ charge, sulfur has a 2- charge. So in order to get a neutral ionic compound, we would need to have 2 aluminums and 3 sulfurs. Cesium and phosphorus. Cesium is a +1 charge. Phosphorus as an anion is a -3 charge. Oh, excuse me, that's cerium. So CS3P. And then barium and nitrogen. Barium is a 2+. Nitrogen is a -3. And so in order to combine those properly, we would need 3 barium to 2 nitride ion. Okay, that's it for this video. Thanks for watching. Have a great day.